Okay, is the screen visible to all of you?
Yes, sir.
All right. Okay, so in our previous class, we just stopped the point where we were talking about the various components that are used for transmitting optical signals from let's say transmitter to receiver, or let's say from one location to another. So we use what is called as a waveguide. So we use what is called as a waveguide. We use what is called as a waveguide for sending information signals from transmitter to receiver. So waveguides are the channels that carry electromagnetic signals or information signals from one location to another. And in the context of optical communication, there are two classes of waveguides that can be used for sending and receiving optical signals. So one is called as a cylindrical waveguide, which is basically an optical fiber. So optical fiber is a is a cylindrical waveguide, or rather a circular waveguide. And you know that an optical fiber is constructed by having a core and having a cladding, and the core having a slightly higher refractive index compared to cladding. And you know that the light rays propagate through the optical fiber by undergoing total internal reflections. And you know that there is a certain critical angle up to which total internal reflection can happen. So an optical fiber is a cylindrical waveguide that is used for sending and receiving optical signals. The other class of waveguide is what is called as a planar waveguide, which we had just which we had seen in our previous class. So a planar waveguide is usually having a rectangular geometry. It's called as planar because the plane of the direction of propagation and the direction of propagation is parallel to the plane of the optical waveguide. So here also you are going to have a core. You are going to have a this white region is having a slightly higher refractive index, the core, and you have the other region, the yellow region, which has a slightly smaller refractive index, and you call it as the cladding. So an optical fiber is constructed by using a core, which is and since this is having a circular geometry, this core is encapsulated by a material called as cladding, which has a slightly smaller refractive index. Whereas in the case of a planar waveguide, you have a slightly higher refractive index. You have a slightly higher refractive index region that is sandwiched between two smaller refractive index materials. And in this case, the light, again, it undergoes total internal reflection. So here you can see two distinct interfaces at which total internal reflection happens. And we also discussed about the various theories that can be used for describing how the light propagates inside an optical fiber or an optical waveguide. So you can classify the theory that can be used to describe them as the ray theory or the wave theory. So one is ray theory versus the wave theory. So ray theory is used when the wavelength of the light is much smaller than the device dimension. In that case, you can use ray theory to somewhat accurately describe, not accurately, but you can decently describe how the light propagation happens. On the other hand, if the wavelength of the light is of the order of the waveguide dimension, or in other words, the waveguide dimension is much smaller than the wavelength of the light, then you will have to use wave theory. So if this condition happens, if d less than is much smaller than lambda, where d represents the thickness of this waveguide. So this thickness of this waveguide. So in the planar for a planar waveguide, this d represents the thickness of the waveguide, whereas in a in a optical fiber, d represents the diameter of the optical fiber, or even the radius. dimension approaches the wavelength of the light, then you will have to use the wave theory. So this is used for wave theory, and this is used for ray theory. And each approach has its own advantages and disadvantages. The advantage of ray theory is that you can simply use a ray to explain how light propagates. So it's much easier for the layman to understand. Whereas the disadvantage is that it's not really an accurate way of describing how signals propagate inside optical fiber. Whereas the wave theory gives you an accurate description. If you want to really understand how if you really want to understand how the modes are distributed or what is the shape of the mode, then it's always better to use wave theory. The disadvantage is that wave theory is more complicated, is more tedious. You'll have to solve Maxwell's wave equations, and therefore it becomes slightly complicated. So those are the advantages and disadvantages of wave theory and wave theory. So I'm just giving you a recap for the 2 or 3 lectures. We are going to describe the electromagnetic theory of or optical signals to planar dielectric waveguide. So we are going to describe how the wave propagation happens inside a planar waveguide. The reason why we are discussing planar waveguide is because rather than optical waveguide is because though in fact both optical fibers and optical fibers which has a cylindrical geometry and the planar waveguide which has a planar geometry, both are waveguides. So that is one reason. So both are waveguides, and if you can explain how, if you can understand how light propagation happens inside a planar geometry, and then it's very easy for you to extend that concept to a cylindrical geometry. The only difference is that in this case we are going to describe the solving of Maxwell's wave equation in rectangular coordinates, whereas in this case the only difference is that you'll have to solve it in circular coordinates or in circular geometry. So this is going to be slightly complicated, but nevertheless the principles, the fundamental principle remains the same. And since we don't have much time to spend on optical communication in this course, we are going to discuss about light propagation in planar waveguides. And if you can understand how light propagation happens in planar waveguides based on the Maxwell's wave equation approach, then it's nothing complicated to extend that to the cylindrical geometry, which is in the case of an optical fiber. So we are going to describe the electromagnetic planar dielectric waveguide. The reason for doing this is we need to understand why we are so the reason why we are interested in Maxwell's wave equations is because we want to understand how modes are distributed, or what is how modes are distributed inside an optical waveguide, and also you want to understand what are the shape of those modes. So you want to know what are the shape of the modes? What are the shape of the modes that are going to be supported by a planar waveguide?
Sir?
Yeah.
Sir, your voice is breaking, sir.
Yes, sir.
Voice is breaking?
Yes, sir. It is
Yes, sir.
1 or 2 second pause and then coming.
How about now? Is it still breaking?
It's fine now, sir.
Okay. Okay, so we are interested to understand the shape of the modes, and you know what are modes? Modes are basically the way in which the electric fields and the magnetic fields of the optical signals are being distributed inside the optical fiber or the optical waveguide. So we are going to solve the Maxwell's wave equation for this planar waveguide, and this planar waveguide can be represented by using this picture. So you have a so if you look at this figure, you have three layers. You have a core layer which is represented by the white color, and then you have two cladding layers that are surrounding that of refractive index N2, where the N2 is slightly smaller than N1. So rather than instead of a three-dimensional picture like this, I'm going to represent this by a two-dimensional figure like this. So this is the figure. This is a two-dimensional representation of a planar waveguide, and you know that in the center region. So this region is you call this as the core. So I would also call this as the guiding layer, because that's the layer, or that's the material which is going to guide the electromagnetic signals. So you call this as the guiding layer. So the guiding layer is going to have a refractive index Ng. The upper layer, or the upper cladding layer, so this is also cladding, this is also clad, this is also clad. So we are going to consider a generalized picture where you have one material for the core and you have two different materials for the cladding. So I'll call this as cladding 1. I would call this as cladding 2. And the cladding 1 is in fact called as the cover layer, and the cladding 2 layer is called as a substrate layer. You would understand the importance of using the word substrate and cover if you can recall how a laser diode or how a semiconductor device is usually constructed. So you know that a semiconductor device is usually constructed on a substrate. Substrate is the one which carries the entire thing, which carries the entire device. So so you call this as the substrate material, and the substrate material has a refractive index of Ns, and the guiding layer, which is the core layer, acts as it has a refractive index of Ng. The cover layer has a refractive index of N. And I'm going to describe the coordinates. The wave propagation happens along the z direction, so along this direction. So I mark it as the z direction, or the z axis. The y direction is represented by a direction outside the screen. So this is the y direction, and the x direction is represented like this. This is the x direction. So this thickness is going to be d, and therefore this one is going to be plus d by 2. This one is going to be minus d by 2. So this represents the origin. So this is the x-axis. This is the z-axis along which the wave propagates, and this is the y-axis. So you would see that you would see that the refractive index. So this is a three-dimensional. So a planar waveguide is actually a three-dimensional waveguide. That means it can have a refractive index variation along x direction, along y direction, and also along z direction. But if you look at our particular problem, the planar waveguide what we have considered, you would see that along the z direction there is no refractive index variation. So you would see that along the z direction the refractive index always remains a constant, and therefore n is as x comma y comma z. But since along z direction there is no refractive index variation, I'm going to represent the refractive index profile only along x and y direction. Only along x and y direction, and you would see that along the y direction also you would see that the refractive index basically remains a constant. So along this direction the refractive index basically remains a constant. So along you would see that from minus infinity to plus infinity along the y direction you would see that the refractive index basically remains a constant. But the refractive index variation happens only along the x direction. So you would see that outside the plane of the screen, the refractive index remains a constant. Similarly, inside the plane of the screen, the refractive index remains a constant. Whereas along the x direction, you would see that the refractive index changes. Now, how does it change? Between plus d by 2 and minus d by 2, you would see that the refractive index is going to be ng. So between minus d by 2 and plus d by 2, the refractive index is ng. From plus d by 2 to infinity, so from plus d by 2 to infinity, the refractive index is going to be nc. And from minus d by 2 to minus infinity, the refractive index is going to be ns, which is the substrate. So this is how you define the refractive index profile for this planar waveguide. So any questions so far? So if no questions, okay, we'll proceed. All right. So you have a planar waveguide like this. Now in this case, you would see that the cover refractive index and the substrate refractive index is different. That means the guiding layer is sandwiched between two cladding layers, but each of these cladding layers have a different refractive index. So if the top refractive index is different from the bottom refractive index, these kind of waveguides are called as an asymmetric waveguide. You call it as an asymmetric waveguide. So asymmetric waveguide refers to the case where the cladding refractive index and the the cover refractive index and the substrate refractive index are different. Whereas if these two refractive index are the same, you call it as a symmetric waveguide. You call it as a symmetric waveguide. So please always have a core and a cladding. Usually the core will be having a larger refractive index compared to the cover and the substrate refractive indices. So if the cover refractive index and the substrate refractive index are the same as the symmetric waveguide, if they are different, you call it as symmetric waveguide. If Ng, so Ng is always going to be greater than Nc and Ns. The refractive index of the guiding layer is always greater than the cladding. Yeah.
Sir, your voice is breaking again, sir.
Voice is breaking. I can't do anything other than just disconnecting and reconnecting once again. So maybe I'll try that. Is it still worse?
Yes, so now it is still there, I think.
No, sir.
Sir, I
It's
mean,
still breaking.
in between, it's going and coming back. Momentary.
Yes, sir.
It's still breaking. Okay, then let me disconnect and once again try to reconnect. Yeah, can you all see the screen now? I hope the voice is better.
Yes, sir.
Yes, sir.
Yes, the screen is visible.
Yes,
sir.
sir.
Yes, sir.
Okay. Yeah, all right. So in this case, the guiding refractive index is always greater than the cover refractive index and the substrate refractive index. So that if you launch a light ray which obeys the
Sir, you are not audible.
Yes, sir. You're not audible.
Yes, sir. Excuse me, sir.
I don't know, today the internet quality is pretty bad. Okay, so if you are launching a light ray which obeys the maximum acceptance angle, then you would see that if the core refractive index is larger, you would see that the ray would undergo multiple total internal reflections at the first interface and the second interface, and it would keep on propagating. So for this condition to happen, Ng should be always greater than Nc and Ns. So the concept of critical angle is valid only in cases where the light leaves a denser medium and is trying to enter a rarer medium. So only in that case you can define what is called as the critical angle. All right. So we are going to analyze the planar waveguide. We are going to analyze a planar waveguide having this particular configuration. And what are we basically going to do? We are going to solve. We are going to solve. We are going to solve the Maxwell's wave equation. The Maxwell's wave equation for the planar waveguide. So for the planar waveguide, which has a refractive index profile that is shown in this particular figure. So that's what we are trying to do. So to begin with, how we solve the Maxwell's wave equation, let us first begin with a classical wave equation. So the Maxwell's wave equation can be written as del cross E. So del cross E is equal to minus dou B by dou T. That's the first curl equation. And del cross H is equal to dou D by dou T. So del cross H is equal to dou D by dou T. And you also know that if you have a dielectric medium, so please remember our optical fiber is a dielectric medium. It's not a conductor, it's a dielectric medium. So in a dielectric medium, we are assuming that in this medium, we are assuming that there are no stored charges. If there are no charges, then there should not be any electric current that is flowing, because electric current is because of charges that current is nothing but the motion of charge carriers or charges. Since there are no stored charge carriers, and because there are no stored charge carriers, you should not be having any electric current, and as a result, using those two conditions, you can write the Maxwell's wave equation as del cross E is equal to minus dou B by dou T, del cross H is equal to dou D by dou T, and del dot B, so del dot B should be 0, and also del dot D should be 0. So we are writing this because this is a dielectric medium. So a dielectric medium with no stored charge carriers or with no charges. Dielectric medium, no charges, no stored charges. And you also know these relationships. You know that D is equal to the displacement current is equal to epsilon into E. You also know that B is equal to mu naught into H. So in the Maxwell's equation, what we have written, so this E and H, so this E and H, so they are the electric field and the magnetic field vectors. Vector means electric field and magnetic field is going to have a direction. You can have a particular orientation for the electric fields and the magnetic fields, and you call them as the modes. So we are going to see. So once we solve the wave equation for this particular waveguide, we are going to see how the modes are going to be distributed. And if you know how the modes are being distributed inside the optical fiber, you can really understand how the information signal is being distributed inside an optical waveguide or an optical fiber. So E and H represents the electric field and the magnetic field vectors. And this B and D, this D and B, so this D and this B, so they represent the electric and the magnetic flux densities. So they are the flux densities, and you know that epsilon and mu naught. So epsilon represents the dielectric, it represents the permittivity, it represents the dielectric permittivity, and mu naught, it represents the dielectric permeability. So this is permittivity. So this is permittivity and this is permeability. And you know that if you have a dielectric medium, then the relative permeability is almost 1. And therefore, it should actually be B is equal to mu into H, where mu is equal to mu naught into mu r, but mu r is going to be 1, and therefore I have written B is equal to mu into H. So we are going to begin with these Maxwell's equations. So you might have studied this in your third semester. All right. So what we are going to do is we want to see. So the main aim of the reason why we are solving all this Maxwell's equation is to understand how the modes are distributed. See, we are going to see how modes are distributed inside. How modes are distributed inside, and what are the shape of those modes. So these are some of the information what we are going to get if you solve the Maxwell's wave equation. So to begin with, we first take the curl of the very first equation. So you have this del cross E. So I'm going to take a curl. So that means del cross E should be equal to del cross minus dou B by, so del cross minus dou B by dou T. So if you use the vector identity, so del cross E can be written as del dot E minus del square E. That should be equal to minus dou by dou T of del cross B. And we already know that del dot E, this is 0. Because D is equal to epsilon into E, which means del dot E is 0. This becomes 0. This is 0 because del dot D is equal to 0. And therefore, what are you going to get? So this would lead to del square E is equal to dou by dou T of del cross B. So a Maxwell's wave equation is basically, so on the left hand side, you're going to have a space derivative. You're going to see how the electric field is going to change with respect to the spatial dimensions. Whereas on the right hand side, because of these spatial variations because of the spatial variation, you are going to have a wave that is going to propagate in time domain. With respect to time, you are also going to have a change in the magnetic field. That is what wave equation basically is. It's going to relate the second derivative of space with respect to the second derivative of time. So now what we are going to do is, you have to so this is electric field. So you have to convert, you'll have to once again convert this del cross B into the electric field domain. So how do you do that?
The relation between D and H. So you can put del cross H.
So you know that D is equal to, epsilon into E, which is basically epsilon naught epsilon R into E. So you can use those relationships, and you can show that. I'm not going to do the entire steps, but you can show that del square E is going to be del square E is going to be mu naught into epsilon into dou square E divided by dou T square. So del cross E will be equal to mu naught into epsilon into dou square E by dou T square. So how we got this is simply by using these two relationships. So you know that, so you can use, so D is equal to epsilon into E. So you can substitute this D is equal to epsilon E in this relationship. So you would get, so from the second curl equation, you know that del cross H Del cross H is equal to dou by dou T of B is epsilon into E, which becomes epsilon into dou E by dou T. And you know that B is equal to mu into H. So use this relation. B is equal to mu naught into H, which means H should be 1 by mu into B naught. So I'm going to write del cross H can be substituted by B by mu naught. B by mu naught. So this would be equal to epsilon into dou E by dou T. Or in other words, del cross E becomes mu naught into epsilon into dou E by dou T. So del cross B becomes mu naught into epsilon into dou E by dou T. So I'm just going to substitute this del cross B, I'm going to substitute with this one. And since mu naught and epsilon, they are not going to change with respect to time. We are assuming that they are not going to change with respect to time because it's a dielectric, it's a constant dielectric, and therefore the time derivative can be attributed only to the electric field quantity, electric field vector, which makes it as mu naught into epsilon into dou square E by dou T square. So you get this relationship. I hope all of you are clear with this. So any questions? All right, fine. Now this epsilon can be written as, so del square E is equal to mu naught into epsilon can be written as epsilon naught into epsilon r. So this can be written as epsilon naught into epsilon r into dou square E divided by dou T square. So mu naught into epsilon naught into epsilon r, where epsilon r represents the relative dielectric constant of the material of your optical waveguide. Now we are now going to solve the Maxwell's equation for a dielectric waveguide, and we are interested in the light propagation. And in the context of light propagation inside dielectric material, what we are more interested is, we are actually more interested in the refractive index of the material. So we would like to, now these are all universal constants, mu naught and epsilon naught, they are constants. What we are interested is, we are going to replace this epsilon r with the refractive index of the material. We are going to replace epsilon r with the refractive index of the material, and we have already seen that the refractive index of the material is not a constant, rather the refractive index of the material is spatially dependent. How does it spatially, I mean, what is the spatial dependence? The spatial dependence is given by this particular relationship. And how do you relate the dielectric constant with the refractive index of the material? The dielectric constant epsilon r is always the square of the refractive index. This is a fundamental relationship what you all should remember. So the square of the refractive index in fact gives you the relative dielectric constant of the material, and this refractive index of the material is defined for this particular waveguide by this particular fashion. That means this equation what we have just written, that means this equation del square E is equal to mu naught epsilon naught epsilon r, this can be written as del square E is equal to mu naught epsilon naught. So epsilon r can be written as n square, or in fact n of x comma y square into dou square E divided by dou T square. So I'm going to replace epsilon r with n square of x comma y. And how do I define n of xy? So n of xy is defined like this. That means you can write, instead of one Maxwell's equation, you can write three Maxwell's equation for these three layers. You can write one for the guiding layer, which includes Ng. You can write another one for the cover layer. You can also write a third one for the substrate layer. So if you do that, you are going to get three Maxwell's equations, which can be written as del square E. So del square E is equal to mu naught epsilon naught into Ng square into dou square E divided by dou T square. And this is valid for minus d by 2 less than x less than d by 2 and minus infinity, less than y less than plus infinity. Similarly, so this is for the guide layer. This is for the guide layer. And for the cover layer, you can write it as del square E is equal to mu naught epsilon naught NC square dou square E divided by dou T square, and this is valid for infinity less than d by 2 less than x less than infinity and minus infinity less than y less than infinity. This is for the cover. And similarly for the substrate, we would write del square E is equal to mu naught epsilon naught ns square dou square E divided by dou T square, and this can be written as minus infinity less than x less than minus d by 2, and similarly minus infinity less than y less than infinity. So what we have done is instead of using one Maxwell's equation, we have used three Maxwell's equation. The reason is because your waveguide is having three layers, and each of these layer has a different dielectric constant and therefore a different refractive index. So which means that the way in which the signals are distributed inside the waveguide would be different for the guiding layer, would be different for the cover layer, and would also be different for the substrate layer because their refractive index are different. If all these refractive index were the same, you would be having only one Maxwell's equation. But since you have three layers, you are now going to have three Maxwell's equations. So now our job is to solve these three wave equations with the appropriate boundary conditions, and we would do that in our next class. All right, so any questions so far?
Sir.
Yeah. Yeah, go on. Any questions?
No, sir.
All right, okay, then we'll stop here. We'll continue in the next class. Okay, thank you all.
Thank you, sir.
लैब है क्या आज?